Steve and I were talking about this. For some reason, it gets harder every year to learn names. I don't know what the holdup is. Maybe there's just too many old names that I need to get rid of. But anyways, you have to kind of bear with me. I am turning worse and worse with names, which is weird because it's supposed to be one of those things like if you practice, you get better at it. But here I am, not getting any better. In fact, getting worse. So you'll have to help me out. But I tried. All right. So I still have one copy of assignment 2. Hopefully everyone has one. Otherwise, I can use that one to photocopy upstairs after class if you want. Assignment 2 is a little bit tricky, right? Not like assignment 1. Assignment 1, I'm really happy with what you guys put out there. It was really good. So I'm not worried about that stuff. But I know assignment 2 can be a little bit tricky, right? Chapter 2 is a little bit, what? And so assignment 2 is due on Wednesday. Right. I have office hours today. I think I made it 9:30 to 11. But we'll be there until 1. I think I only made it to 11 because when there's stuff due, yeah, people show up. Otherwise, I'm just kind of sitting there and I can't go get lunch and I can't go do anything. And so I made it short, but of course, kind of if you're looking at my schedule and it looks like I might be there, I'm probably there. Okay? And so I'll also be here all day tomorrow. And so available anytime tomorrow. Definitely 9 to 5. I'm usually heading home around 9. But anyways, so definitely 9 to 5. And I usually try to get here between 7 and 7:30. But that's kind of my time. I do marking and I do all these tinkering things. But anyways, so definitely between 9 and 5 tomorrow should be plenty of time. But if you need me at a different time, then just let me know. I am way over in the C building, so you can text 250-864-8386 to make sure I'm there. So if you need help with assignment 2 or what have you, then we can go through that. Okay. So we won't do any review because that's kind of, we finished, I guess that is the review. We finished chapter 2. Finished chapter 2. For chapter 2, we only did 2.1 and 2.2. If you're ever referencing the textbook, it goes deeper into chapter 2, but we pull the plug. So 2.1 and 2.2. And of course, it's feast or famine. So now I have 3 extra printouts of chapter 2. Anyways, I didn't get one. I have some. So today we're going to start chapter 3. But are there any questions about chapter 2 that you think might apply to everyone? Yeah. Oh, we didn't finish chapter 2. I lied. didn't I? It's all coming back to me now, as Celine Dion said. Okay, all right. Finishing chapter 2 today. How about that? You know what I'm going to do then? I am going to nope. I'm going to steal this because you have it in your notes, presumably. What a little curveball to throw you. Sorry, guys. Recall. So we developed this tree diagram, right? And we said to find the probabilities at the end of each branch, we just multiply down each branch. Right? And that's how we found each of these probabilities. And then we said, well, because this is all possible outcomes, then the total must be 1. Right? And so we can make sure, and the total has to be 1. On your assignment, right, here we're talking about 2 consecutive events, right? And on the assignment, you're going out for 2 consecutive days, right? So you're gonna have day 1, day 2. Have a sighting or you don't. And so your probabilities actually will stay the same for the yes and no's, right, for each of the branches, so they don't change, so it's a simpler problem. Yeah. Let's see, what were the problems that we had to solve? 2. So this is one, I think. Build the tree diagram with all the appropriate probabilities. And by that, I mean the probabilities at the end of each branch, right, as well as all the individual probabilities. What's the probability of a student earning an A on both the midterm and the final? So we want to know what's the probability of M and F. Both the midterm and the final. So now we can look at our tree, right? And we say, okay, well, we have to get an A on the midterm, so we have to go down this branch. And we have to get an A on the final, so we have to go down this branch. And so the only way that that can happen is 0.13 times 0.47, which we decided was 0.0611. So once you've developed this tree diagram, then it's a lot easier to answer these questions, right? Because then you can just say is equal to 0.0611. You don't have to show any work because you did in your tree diagram. On your assignment, I think each of these parts is worth 2 points. But in reality, right, the tree diagram would be worth more points. And each of these little questions that you're answering would just be 1 point. So 3, what's the probability of a student earning at least 1 A on either the midterm or the final? Okay. So what's the probability of at least 1 A? Okay. So now we're gonna look, you can look down the branches, or that's why I like to have these kind of summarized down here, right? Because the complements mean they didn't get an A, right? So any of these M and F, that's two A's, right? Here's one A. Here's another A, right? And so all of these situations, here's at least one A, we got two A's. Here's at least one A, they got an A on the midterm, but not on the final. Here's at least one A, they got an A on the final, but not on the midterm. The only one where it's not happening is where they didn't get an A on the midterm. They didn't get an A on the final. Right? But these three all satisfy that criteria of at least one A. Right? So what we can do is we can say, well, that's the same as the probability of MF, right? Plus the probability of M not F, plus the probability of not M F. Whenever you find yourself saying or, so this, or this, or this, you're going to be adding things up. Whenever you find yourself saying and, right, so scroll down here, midterm and the final, you're multiplying. So that's a good kind of check-in point. So I'll just make a note of that down here. Note. Whenever you say and, you will be multiplying. And whenever you say or, you will be adding. Right? So I'll just make an arrow here. Or I'll need some more room here, so I'll scoop my equal sign over. Okay. But we have 0.0611. So the tricky part is figuring out which of these branches satisfies that criteria. And then after that, we can just pull all our probabilities from the tree that we've already made. So M and not F was 0.0689 plus not M and F 0.0957. I didn't bring those Martha Stewart notes. 0.0611 plus 0.0689 plus 0.0957. 0.2257. What's another way you could have gone about this question? We could have said, well, right, we already decided that these three are the ones we want. Right? So instead of adding up this one, this one, and this one, those probabilities, right, we could say, well, the total has to be 1. Right? So what if I just pull out the one that doesn't satisfy that criteria, and that's going to get you to the same answer. And so that's a trick that we don't really need for this section, but it is a trick that we'll need for later sections when we do the binomial, right? Then we'll need to think, okay, well, is it going to be easier to just look at the complement of at least 1? Right? And so here, I almost said or, but I'll say alternatively, we could take the complement of at least 1A and subtract it from 1. So then we have the probability of at least 1A is 1 minus the probability of not the midterm and not the final. It's going to be 1 minus 0.7743. Puts you at 0.2, oops, 2257, which is the same. Can't have them on the same screen. But. So there's easily two ways that we could get to this answer. Any other way would be too elaborate, right, and too difficult. There are other ways, but we don't need them. So for that one, whichever way you prefer is fine by me, as long as you show me what you're doing, then and I can follow it, then you're good. 4. What's the probability of a student earning an A on the final but not on the midterm? Probability of just because we have our M's first, right? So not on the midterm, but an A on the final. There's only one situation that can get you there, right? If you look at your tree. So we're saying, okay, we have to get an A on the final. That's these two branches here. Right? But then we're saying, but we also can't get an A on the final, right? So then we're back to just one branch satisfying that. And so 0.0957. 0.0957. Great. Hopefully that helps with your, should help a little bit with your assignment. Thank you for reminding me. Sink or swim around here, guys. No, I just forgot. All right. Any questions? No? Okay. Now we'll start chapter 3. So 3.1 is the normal distribution. Which we've already seen, right? But now we kind of, it gets a little bit annoying because we talk about the normal distribution and those concepts we're going to use throughout the course. So this section is really important, and that's why we're going to spend this week on it, right? Just kind of solidifying the normal distribution, how it behaves, things we can do with it. Because in the end, we're going to use this normal distribution to find probabilities. Right? So different kinds of probabilities, but those are the probabilities that we're going to deal with throughout the course. So they won't be like those tree diagrams or anything. But as you'll see, so next week, we kind of pop into the binomial distribution, which is a different distribution. And it's kind of annoying because it puts a wrench in our normal distribution plans, but then it snakes back in. So we kind of start the normal distribution, pop out, do the binomial, which is going to feel weird, but it's going to link together eventually. And then we keep going with the normal distribution. Maybe it's good to leave it for a bit, let you guys think on it, do an assignment on it probably. Come back to it. Okay. So we said that if we have a normal distribution, right, we're better off using the mean and the standard deviation as our measures of center and spread, right? We've developed that already. So recall, if we have a normal distribution, we should use the mean and standard deviation. We should use the mean and standard deviation which here I'll abbreviate to SD because we'll be writing standard deviation a lot. So I'll officially define it there. As our measures of center and spread. Measures of center and spread. So in this section, we're really just going to develop why that is, right? So in this section, we will discuss some of the tools we have through the mean and standard deviation. Through the mean and standard deviation. Okay. So remember, we already talked about it, right? But we said X bar, that's the sample mean, right? Because now that we're talking about the mean and the standard deviation, we really have to keep track of, okay, what's from the sample and what's from the population. Right? So X bar is the sample mean. Mu is the population mean. Lowercase s is the sample standard deviation. And lowercase sigma is the population standard deviation. So we'll start this section, I'll tell you some facts, and then we can talk about them. So here's a fact that regardless of what the mean and the standard deviation are, right? So regardless of if it's 1,000 for the mean and 300 for the standard deviation, or 1 and 3 for the mean and the standard deviation, it doesn't matter what the mean and the standard deviation are. Just as a fact, the normal distribution will be centered on the mean, right, which we've kind of talked about already, right? But also we'll be able to fit 3 standard deviations on either side of the curve before it closes off almost completely, right? It never closes, but basically completely. Okay? So regardless of the mean and standard deviation, the normal distribution will always be centered on the mean. Centered on the mean. And fit 3 standard deviations on either side of the mean under the curve. 3 standard deviations on either side of the mean under the curve. So what that looks like, I'll draw a nice big normal distribution here. Try to at least. Here in the center, we have our mean. And I'm just talking about the population mean and the population standard deviation. But it works for the sample too, but for this, I mean the population. So here we are. We've got this one under control, right? This one we were okay with. So the normal distribution is centered on the mean. Fine. So that means that we draw a line down the middle, and that's where your population mean is. This part though, and we can fit 3 standard deviations on either side of the mean. So the distance of the standard deviation is the same. So here, here, here. That worked out pretty well. And so we're going to have 3 standard deviations on either side. So what that's going to look like is you're going to have kind of a line here, a line here, and a line here. And this here is going to be mu plus sigma. You've got a distance of sigma, the standard deviation. Here, you're going to go to mu plus 2 sigma, right? You've gone 1 sigma, 2 sigma up from mu. And then here, you've gone 3 sigma, mu plus 3 sigma. Let's draw these down a little bit so they don't get so crowded. Mu plus 3 sigma. Notice how there's still room here. We'll talk about how much room there is there. It's not very much. Because technically these tails never close on the axis. What we'll learn is that the area under the curve is a probability. So if this never closes on the axis, it's just saying, well, there's a probability of that thing happening. It's just really extreme. And so that's kind of what we'll talk about this whole week. And so same thing on the other side, we can fit 3 standard deviations on the other side as well. Right now we're going down from mu. So now we're going to, let's see, mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. Got a little sloppy towards the end, but that's the idea. So that's a fact. In business, there's this thing called 6 Sigma. It's like a business philosophy, something or other. I don't know too much about it. Has to do with this, right? We can fit 6 sigmas underneath the curve. So that's where we should be hanging out, right? Not in the tails. So, lock that fact in. We'll come back to it, right? But here are some more LFFs, little fun facts. About the normal distribution. First one, we've already kind of talked about, is that the tails of the normal distribution extend from negative infinity to positive infinity. So these tails, right, go on forever. And it's kind of like the idea of anything can happen. Right? So it's just leaving room. And they never close on the axis. So the tails of the normal distribution extend from negative infinity to positive infinity and never close on the axis. And never close on the axis. So we can add that fact onto here. Just say that that would continue to positive infinity and this would continue to negative infinity. So here, our second fact, which we've also already said, right? But we have to write it down. The area under the curve is a probability. So the area under the curve is a probability. So what we'll work towards is something like, well, what's the probability of landing 2 standard deviations above the mean? That probability is this area under the curve. So we find the area that corresponds to what we want to talk about. But we'll get there. If we know one thing about probabilities, it's that the total probability has to be 1. Right? If you've looked at all the possible outcomes, the total probability has to be 1. And so the total area under the curve is 1. The total area under the curve is 1. That's a little bit mind-boggling, right? Because we said that these tails never close, right? But we'd have to use calculus to prove it, but just trust me, the total area is 1, right? And it's just kind of a cool property. Hard to wrap your head around, but it's just how it is. This one kind of goes without saying. The normal distribution is symmetric about the mean, right? But I want to mention it here because we actually use that fact quite a bit. Right? And so the normal distribution is symmetric about the mean. Okay. Those are all the facts for now. I'll add some more later. But for now, Well, I guess the others are just concepts. So those are the facts that we have to keep in mind when we're using these normal distributions to find probabilities. Okay? So let's just, so we use the area under the curve to find or calculate probabilities. We use the area under the curve to find / calculate probabilities. If you guys have your formula sheet, we probably won't get there today, but I want you to have a look to see where we're headed. To find these probabilities, we're going to end up using this table A, the Z table. And so it just has all these probabilities, and we'll talk about how do we use this table, right? So this is where we're headed. But first, I want to talk about how do we approximate probabilities, because that's useful too, right? Being able to approximate these, and then if we want more specific probabilities, then we can use this table A, the Z table. Okay. So you don't need it right now, but if you don't have a formula sheet, you can grab one after class. So, like I said, you don't need one for now. Just know that that's where we're headed. But first, we're going to just talk about how do we approximate these things. And I don't know. I'd like to think that I'm pretty new school, so I actually don't think that we should be using these Z tables anymore. They're pretty archaic. We don't need them. We can just use the approximations and then use R to calculate probabilities, more precise probabilities. But it's my job to teach you how to use the table, so here we are. But just so you know, right, you don't need the Z table. You can just use the approximations that I'm about to show you. Right? On assignments, of course, I need you to show me that you know how to use the table. That's why we're covering it. Okay? So to approximate areas under the curve, we use the 68, 95, 99.7 rule. I like calling it that because once you kind of have that ingrained, then you also know the probabilities. 68, 95, 99.7 rule. It's also called the empirical rule, aka the empirical rule. But if you Google the 68, 95, 99.7 rule, they'll know what you mean. Right? So you don't have to Google the empirical rule, but if you see something about the empirical rule, then you'll know that they're the same. And so what this rule says is that if we have a normal distribution, so it hinges on having a normal distribution. So we have a normal distribution centered on the mean. And again, we've got 3 standard deviations on either side, right? So 1, 2, 3. 1, 2, 3. Here we've gone to mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. Here we've gone to mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. gets tricky to draw this, right? So I'll just talk about it. What this rule says is that if you've moved, well, first let's talk about, is the area of this space the same as the area of this space? No, right? And you can't just cut it in half because we've got this slope here. Don't really know what to do with that. And so that's one thing that you need to keep in mind, is that this space is not the same as this space, right? The size of it. And so what this rule is saying is that if you go out one standard deviation on either side of the mean, right? So from the mean, you go out one standard deviation, you've captured the central 68% of the curve, or 0.68 out of the total 1. Just knowing that, right, I could ask you, well, what's the area below this point? Then we would say, well, because we've got the central 68 here, then I've got 32 left over, split evenly amongst the tails. Don't worry, I'll write this down, right? Just talking about where we're headed. Right? And so then we have 16 or 0.16 in each tail. Right? So then the probability of being less than u minus sigma, for example, 0.16. So that's how we can just approximate areas under the curve. I want you to think of these little pieces as individual puzzle pieces. And because, so this is why we wrote down that it's symmetric about the mean. So because it's symmetric about the mean, knowing that this area is 68, right, then we've got 68 divided by 2 in this section, and 68 divided by 2 in this section, right? Split in half. So between one standard deviation on either side of the mean, we've got 68% of the curve. Okay, here we're talking percentages. It's nicer to talk about. If we move out 2 standard deviations, now we're between here and here. We've got the central 95%. That's a good chunk of the curve. So within 2 standard deviations, we're expecting to see 95% of our data. That's a lot. So don't have to go very far to capture a lot of what we're expecting to see. And then if we move out 3 standard deviations, we're out here in the tails, right? 3 standard deviations. We've got the central 99.7%. So even though it looks like there's a lot of room here and here, I just do that on purpose to show you that there is a little bit of room. But how much would there be? There'd be 0.3% split evenly amongst the 2 tails. It's between here and here, you've got 99.7. So then you have 0.3% split evenly, so you have 0.15% in each tail. So what that's telling you is that the probability of being more than 3 standard deviations above the mean, right, at this point, is 0.15%. Right? That's tiny. So it's very unlikely. It's possible, but it's very unlikely. And so that's how this approximation is going to work, right? We can just break up our curve into standard deviations, and then we can talk about these puzzle pieces. I think of them as puzzle pieces. So, well, it gets tricky to draw all that. So you've got central 68%, 95%, 99.7%. So what I'm gonna do is I'll just use kind of like this, just to indicate that this area here is 68%. And then between the two standard deviations, whoops, we've got 95%. I've taught this so many times now, and I still haven't figured out a good way to illustrate all these overlapping areas, right? Because you shade one in, and you shade it in again. I don't know. So anyways, it's kind of what I've landed on, but it's not great. 99.7, oops, %. The 68, 95, 99.7 rule says the central 68% of the curve, the central 68% of the curve, right, I'll put 0.68 out of 1, is within one standard deviation, one SD, from the mean. So really it's between, put in brackets here, mu minus sigma to mu plus sigma. Same thing for the 95 and the 99.7, right? But it's good to have them written out. So the central 95% of the curve, which is going to be 0.95 out of 1, is within 2 standard deviations of the mean. So I'll just put in brackets between mu minus 2 sigma and mu plus 2 sigma. And then the central 99.7% of the curve so that's 0.997 out of 1 is within 3 standard deviations of the mean. So between mu minus 3 sigma and mu plus 3 sigma. So we can use these approximations to find other probabilities. We can use these approximations to find other probabilities. For example, what's the probability of being less than? So what is the probability of an observation being I tried to throw in the observation, but maybe it doesn't work. It doesn't work quite yet. I'm going to strike something here. What's the probability of, without numbers, it doesn't make sense to talk about an observation because then it just makes it less than something else. Anyways, don't worry about it. What's the probability of being less than mu minus 2 sigma? So what we can do is we can sketch out our normal distribution. And as always, so this is always going to be true. It's always going to be centered on mu. And then the point that we're interested in is here somewhere at mu minus 2 sigma. Our approximation requires that we know that here is mu plus 2 sigma. Just do a dotted line there, because the 68, 95, 99.7 rule only says that around the mean, right? So the central 95% is between 2 standard deviations from the mean. So if we're interested in this point, right, then we have to imagine this point, and then we know that this area, right, is 0.95. What you'll find is when we're doing calculations, just work with the decimals. But I find when I talk about stuff, it's easier with percentages. So be fluent, I guess. So here, this area is 0.95. Or you know what? Here, I'm going to shade it. Because on this graph, I'll only have one area. So this area is 0.95. The area in the tails, right, knowing that the total area is 1, then the area in each tail, the area in each tail must be the remainder from 1 minus 0.95, which is 0.05, split evenly between the tails, right? Again, going back to the symmetry, right? So we know that the leftover area must be 0.05, right? 1 minus 0.95. And so we have to distribute that evenly, right? So each tail has an area of 0.05 divided by 2, which is 0.025. And so this probability that we're looking for must be 0.025. Now it's hard to talk about these without actual numbers, so that's why I'm not rewording the question as an answer, because we'll work with real numbers soon. So I want you to think of these areas, right, just as puzzle pieces, and knowing that the total area has to be 1, right, you'll be able to kind of dice up sections and kind of figure out the probability that you need. The whole goal of statistics, why you have to take this course, presumably you all have to take it, you're not here just because you want to, is because we want to be able to analyze or assess if we have extreme values, right? For better or for worse, right? You're testing water, for example, and whatever you're measuring is way too high, right? Is that extreme? You need some way to say, yes, it's extreme because of these calculations, or no, the water's still safe because of this calculation, right? If you're working in sales, for example, my sales were extreme compared to everyone else, right? On the high end, hopefully, if you're trying to make a point, right? And so you need some way to calculate these things. And so our goal is to assess or analyze if a value is extreme or not. If a value is extreme or not. So as a general rule, we're going to say that anything within the central 95% of the population, right? And now from the 68, 95, 99.7 rule, we know that anything within 2 standard deviations, right, from the mean will be considered, I guess, not extreme, right? Kind of within the norm. I hate to say normal when we're talking normal distribution, gets confusing, right? But just kind of where you're expecting things to be, and anything beyond 2 standard deviations would be considered extreme. So as a general rule, we say that a value within the central 95% of the distribution will not be considered extreme. Therefore, if a value is more than 2 standard deviations, away from the mean, and that can be either above or below, right? Doesn't matter either way. Above or below, we consider it an extreme observation. So just like we're starting with the 68, 99, 95, 99.7 rule to approximate areas under the curve, and then we're going to go use the Z table to find more refined areas under the curve, this rule is the same, right? So anything beyond 2 standard deviations as a general rule of thumb will be considered extreme. We'll develop more refined ways to decide if something's extreme or not, right? And we'll do that using the p-values. But for now, and honestly, if you leave this course and this is what you remember, then I'm happy with that. Right? You don't have to remember the nitty-gritty as long as you remember the approximations. At the end of the day, you can just ask someone to look over your work, but it's good to be able to look at something and say, oh, that's 3 standard deviations above the mean. That's weird. How extreme. Right? And so, right, now you know anything beyond 2 standard deviations as a rule will be considered extreme. This kind of means that we have to figure out, well, we need some way to calculate how far something is in terms of standard deviations. And so this means we need to be able to calculate how many standard deviations a value is from the mean. Can give you something as an example. Say the mean is 6 and the standard deviation is 2. How many standard deviations is an observation of 4 from the mean? Start slow. Because I think we could all figure this out, right? If we drew a timeline and we said, okay, well, here's our timeline, or number line, I guess. We can put 6 on here and 4 on here. And we just know that this distance is 2, right? Sigma is also 2, right? And so therefore, 4 is 1 standard deviation away from the mean. And it's, if I want to specify, I can specify below the mean. How about if the mean is 6 and the standard deviation is 2 still, how many standard deviations is negative 4.91 from the mean? Right. We can apply the same method, right? Where all we're doing is finding the distance between the mean and this observation. And then essentially we're just dividing it by the value of the standard deviation. Right? So here we've got our number line. So here's 6. At some point here we've got 0, just throwing that in for good measure. Negative 4.91. This distance is 10.91. So then we have the distance divided by the standard deviation is 10.91 divided by 2. I'm going to go across because it's not that important. 5.455. So therefore, negative 4.91 is 5.455 standard deviations below the mean. So what we use, right, or what we did here is we have to find the distance between these two values. Right? And so we have to find the distance and then we divide by the standard deviation. And from here, what we're actually calculating is what we call a Z-score. And so a Z-score is just a calculation that helps us find how many standard deviations are in this distance. Right? And so to calculate how many standard deviations, oops, how many SDs and I'll put sigma in brackets there. So how many standard deviations, an observation, which I'll put in brackets a lowercase x, because that's how we're going to denote these observations, right? First observation was 4, then we went to negative 4.91, right? So those are the values that we're interested in, right? So those will be our x's. So to calculate how many standard deviations an observation is from the mean, mu, we find the Z-score. And Z is going to be x minus mu over sigma. Notice that this is the distance, right? And of course, this is your standard deviation. So it's exactly what we were doing, right? What if we had to kind of think about it every time, or we can just use the formula and say, well, Z is x minus mu over sigma, and Z tells us how many standard deviations x is from mean, from mu. So for x equal to negative 4.91, mu equal to 6, and sigma equal to 2, Z is x minus mu over sigma, which is negative 4.91 minus 6 over 2, bless you. We get 4.91 negative minus 6, puts us at negative 10.91 over 2, which is negative 5.455. Pardon? Yeah, you bet. Got carried away. This is the same value that we found, right? Except this one's negative. What we'll notice is that a negative value just means that this x is below the mean. Right? Whereas if it's positive, it's just saying that, well, whatever this value is was above the mean. And so here, a negative Z-score means x is below the mean. whereas a positive z-score means x is above the mean. So from this z-score of negative 5.455, we can say that negative 4.91 is 5.455 standard deviations below the mean. So therefore, x equal to negative 4.91 is 5.455 standard deviations below the mean. Maybe we'll save this example for the start of next day. Yeah, that's good. So if you didn't get your assignment 1 back, come grab it. If you need a copy of assignment 2, I can give you this one, or if there's more, I'll need it to make photocopies. Awesome, thanks. Yes.